Okay, so our next topic we're looking at is something called electric potential and potential difference. So just like in gravitation, we first looked at the force due to gravity, and then after that we looked at energy. Same thing with electrostatics. First we looked at forces and electric field. Now we're starting to look at energy. So first thing we're going to look at is, well, let's do a little analogy. So imagine we have a person standing on a cliff, and that person decides to drop a ball, and the ball hits the ground. So when we look at this up here, we had lots of potential energy up here, and down here we lost potential energy as it fell. It fell down, we lost potential energy. So we had lots of potential energy at the top, very little potential energy at the bottom. So now we're going to look at something called a capacitor and charged plates. So how a capacitor works is that if we have one charged plate, that is one plate that's positively charged, and another plate that is negatively charged, we create what's called a potential difference. Basically what it comes down to, though, is on this side we have high potential energy, and over here we have low potential energy. Again, if we put a test charge, some positive Q inside, it wants to go from positive to negative. We get those electric field lines that want to go from positive to negative, positive to negative, positive to negative, positive to negative, like so. So how we can kind of compare gravitation and charge is, imagine if we then put this, if we reoriented that capacitor such that we have the positive plate up here and the negative plate up there, just like how in gravitation where that mass goes from that higher location to lower location. Same idea. It's like, if imagine we had that positive charge that is starting at that positive and falling down to that negative. So just being repelled from the positive end and falling towards the negative. So we have points of high potential energy to points of low potential energy. So let's scroll down. So once we have this thing called potential difference, it's directly related to energy itself. So we've seen that work is force times distance. And this thing we call electric potential, it's also known as voltage, is just the change in potential energy over the charge. So energy per unit of charge. And the thing that tricks a lot of students up is that understanding of what energy is. So again, when we calculate these values for electric potential and potential energy, the number itself doesn't really mean much to us. It's when we actually compare differences in potential, that's when it gets interesting. That's when we can the numbers we can use to actually determine the energy to move from point A to B. At a specific point A, it doesn't actually have much meaning, but it's that change that has meaning for us. So we just scroll down, just working with some equations, just showing that the potential is that energy over charge. Be careful, don't mix up this when we write down that EP right here. That is not electric field. Right now we're just talking about potential energy. Potential energy. Okay. Or if we just wrote down E, this is electric field. They are completely different things. Electric field. So in our formula, see that EP, that's energy over charge. So electric potential is defined as energy per charge. So here is a question. It says, if an object of charge Q moves through a potential difference defined as VBA, so from A to B, its potential energy changes by an amount QVBA, just by giving that formula. So let's draw this picture. So we have a scenario where we have a positive plate and a negative plate. So the reason we're looking at these capacitors first is they have what we call a uniform electric field. So it makes our calculations very simple. We know that the electric field at one location is the same as the electric field somewhere else within that space between the charged plates. Later on, we'll look at when we have a non-uniform electric field caused by point charges. So in this case, it says an electron is accelerated through a potential difference of 5,000 volts between two parallel plates. So when you draw this thing, it could be like this is 5,000 volts, and that's 0 volts. The key thing is the difference of 5,000 volts. I could have just as easily said the following, though. I could have said that this is like 4,000 volts, and this is negative 1,000 volts. Again, it doesn't really matter what those numbers are in itself. It's the difference. The difference is still 5,000 volts. Okay, so we have the difference is 5,000 volts. Let me write that in again. And we have an electron that is accelerated through a potential difference of that quantity. So here's our electron. And we know electric field lines go from positive to negative, but because an electron is going to go in the opposite direction from negative to positive. So work is just the change in energy. It's the same thing. Work is the change in potential energy, which is just Q multiplied by V. If you just multiply that through, our charge is negative 1.6 times 10 to the negative 19 coulombs times 5,000 volts. We get an energy of negative 8.0 times 10 to the negative 16 joules. The question is, why is it negative value? The reason for that is this is negative work. So the charge wants to travel from the negative to positive. If positive work is like if I put energy into the system, I can move it. I can therefore move that electron away from the positive. This one is losing potential energy because the electron wants to go to the positive end. Yeah, so that value, there should be a negative down there. So if we want to look at what's the speed when it gets to the other end, it's like something called conservation of energy. Hopefully you remember that from a previous topic. So conservation of energy. If we're assuming no frictional forces, we know all that potential energy at one side is going to be converted into kinetic energy on the other side when it gets to the other end. So the change in energy is equal to 1/2 mv squared. So if we lost 8.0 times 10 to the negative 19 joules of potential energy, that means we're going to gain 8.0 times 10 to the negative 16 joules of energy for kinetic energy. So that's 1/2. And it's putting the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And we're solving for v squared. So we solve for v, we get a speed of 4.2 times 10 to the 7 meters per second.